In this section, we'll be looking at using Taylor polynomial approximations in order to estimate certain functions at different x values, and then the error bound for what that value is to what the actual value is. That's called the Lagrange error bound. So first, remember Taylor's formula was that you could write the function as f of c plus f prime of c times x minus c plus the second derivative evaluated at c over 2 factorial times x minus c squared, and so on, plus some remainder. So the idea behind the Taylor polynomials is that we'll use all of that except that remainder part, and then the remainder will help us to determine what the error is, what the upper bound of the error would be. So this is what we would use to find that remainder. So whatever degree polynomial we are finding to use for the estimate, the error would be the derivative's degree one more than that. We would determine what u has to be less than when we do this, and so we'll look at an example of that. But we would use this formula for that remainder to determine that error bound. So again, the idea is we're going to take Taylor's formula and we're going to ignore the remainder part. This n means how many derivatives are we going to go to use to approximate what the value of that function is near the point that we want to evaluate it at. So in this example, since we're looking at e to the x, we already in previous section came up for the expansion, the Maclaurin expansion for e to the x, where c is 0. So if you recall, that was x to the k over k factorial, or if we expand that out, 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So our p sub n of x is going to be 1 plus x plus x squared over 2 factorial over 3 factorial all the way to x to the n over n factorial. So that's our expansion for e to the x. And if we look at the different graphs, so a linear approximation would be if we found that tangent line at x equals 0. So we've done that all throughout this class, finding the equation of a tangent line by getting the slope and using that slope in a point. Well, very close to 0, that tangent line approximation is really good. But the farther away we get from 0, the farther away we get from the actual values at e to the x. If we use that equation where n is 2, we get a little bit closer with that equation. Where n is 3, we get even closer the farther away we get. And as n gets larger, our curve that we get for our polynomial is going to get very, very close to e to the x, even farther away from e to the x. So linear approximations are okay as long as you're really, really close to that point. But if you need to use an approximation for a point that's farther away, then you can get better approximations by getting a higher value of n in your Taylor polynomial. So this is going to be using a third degree polynomial, Taylor polynomial. So to do this, we're going to take our f of x, which is the square root of x, or x to the 1/2 power. So f of 1 is equal to 1. Take the first derivative of that, which is 1/2 x to the negative 1/2. Evaluating that, we get 1/2. The second derivative is going to be negative 1/4 x to the negative 3/2. Evaluating that at 1 gives us negative 1/4. And the third derivative is going to be 3/8. When I simplify that, I multiply negative 3/2 times negative 1/4, so I get 3/8, positive 3/8, x to the negative 5/2. And evaluating that at 1 gives me 3/8. So my polynomial, we use f of 1, which is 1, and then we use the f prime of 1 value x minus c over 1 factorial, which is just 1. Then we use the second derivative value, I'm going to make that a minus, x minus c squared over 2 factorial, which is just 2. And then this value, x minus c cubed over 3 factorial, which is 6. So simplifying that gives us gives us 3 over 48 here, which is 1 over 16. So that's the simplified version of our polynomial. And if we look at a graph of that polynomial, along with a graph of square root of x, this is our square root of x graph. This is our third degree Taylor polynomial. So very close at 1 and a little bit past 1 on either side. So in this one, if we're going to do at natural log of x at 1, and we're going to do a fourth degree polynomial. So this time we'll have to go all the way to the fourth derivative. So if we start with f of x is natural log of x, and evaluating that at 1 gives us 0. Natural log of 1 is 0. F prime of x, 1 over x. Second derivative is negative 1 over x squared. Third derivative is positive 2 over x cubed. And the fourth derivative is negative 6 over x to the fourth. And that gives us negative 6 there. So when writing out our polynomial, we take f of 1, which is 0, so I don't need to write that one in. This time, x equals 1, again, like last time. So now we have 1 times x minus 1 over 1 factorial. Then we're going to subtract, so it's negative 1 times x minus 1 squared over 2 factorial, which is 2. Then we have 2 x minus 1 cubed over 3 factorial, which is 6. And then 6 times x minus 1 to the 4th over 4 factorial, which is 24. And again, simplifying that, gives me this polynomial. So that polynomial graphed is this red graph. This is natural log of x. So once again, at 1, we're very, very, very close to being the same. Now, what we haven't looked at yet is the error bound, that Lagrange error bound. So we're going to do that in this next example. So, first part, we're going to do sine x. So again, we already know the Maclaurin the expansion for sine x. We did that, and that was one of the ones in the chart that you should know. So the Maclaurin expansion for sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. We're only going up to 7 because that's p of 7. And remember, the ones in between here were all zeros. So this is our expansion for the 7th. The actual one keeps going, but we're just going to use that for the 7th. So p7 of x is just that first part. So again, looking at a graph of both of those, we're very, very close to sine x, our p of 7. Notice we've gone all the way to 7. So we're really, really close. And we're doing this at x equals 0. So here, if we want to approximate 1.1, we just plug that into this polynomial, or 0.1. We plug that into the polynomial. And when we plug that in, we get approximately 0.0998. So what we've done is we've estimated the value of sine of 0.1 by using this Taylor polynomial. Now we want to see how close is that to the actual value, like what's the error bound, what's the upper bound for an error. So to do that, we take that formula, so it's going to be the 8th derivative of the function evaluated at u times x minus c to the 8th power over 8 factorial. Well, the 8th derivative of sine is just going back to sine again. So sine of u, our x minus c, so x was 0.1, c was 0, is 0.1. And for sine of u, to be able to figure out what that is, Well, we know that sine, the absolute value of sine, always has to be less than or equal to 1. So we can substitute that in for the sine of u in there. And that is approximately 2.480 times 10 to the negative 13th. So that's the upper bound for our error. That's how far away from the actual value of sine 0.1 we are when we use this Taylor polynomial. So that's a very, very good approximation for sine of 0.1. In fact, if we're only rounding to that decimal place, then we haven't made any error at all. So we can use a Taylor polynomial to approximate e, and if we want the error bound to be less than 0.001, we have to figure out what n we're going to use there. So first of all, the Taylor expansion, the Maclaurin expansion for e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial x to the n over n factorial. And then our remainder is going to be e to the x factorial. So u is going to be between 0 and x, and if we want e, we're trying to figure out e, that's the same thing as e to the 1. So x is equal to 1 there. So e to the u is less than e to the 1 because u has to be less than x. And we also know that e to the 1 is less than 3. So that tells us that e to the u over n plus 1 has to be between 0 and this, and so that is less than 3 over . So e to the 1 is going to be equal to that Taylor polynomial evaluated at 1 and the remainder. And that keeps going until we get to that e to the u. So the smallest n for that value right here to be less than 0.001, because remember that's what we wanted our error to be less than. The smallest n for that to happen is where n equals 7. So that means we should use p sub 7 of 1. And so plugging this in, just going up to 7, so we'd be plugging 1 in for x each time, going up to 7 gives us 2.718254. So that's our approximation for E using a Taylor polynomial of 7. And then we know of degree 7, and we know then that that error is going to be less than 1/1000th because we used that 7 and we calculated that that error had to be smaller than that number. All right, in this last one, we're going to use a Taylor polynomial degree of 4 to approximate the natural log of 1.1. And then find the Lagrange error bound. So we have two choices here. We could use that x is equal to 1.1 and c is 1, but that makes our Taylor polynomial a little bit more complicated. Or we could use that x is 0.1 and c equals 0, but instead of using natural log of x, we would use natural log of x plus 1 as our f of x. So then evaluating that at 0 at c gives us 0 for the function. The derivative of this is 1 over x plus 1. Evaluating that at 0 gives us 1. The second derivative is going to be negative 1 over x plus 1 squared. Evaluating that at 0 gives negative 1. Third derivative, 2 over x plus 1 cubed. That gives us 2. And the fourth, negative 6, x plus 1 to the fourth, and that gives us negative 6. So, writing out that Taylor polynomial approximation, we get 0 and then 1 times x over 1 factorial plus or minus 1 times x plus 1, or just x, sorry, because we were evaluating at 0, x squared over 2 factorial, which is just 2, plus, and then we have 2 over 6, which I'm going to just change to 1/3, so x cubed over 3. And then we have 6 over 4 factorial, which is 24. 6 over 24 is just 1/4, so I'm going to change that to 1/4. So that is our polynomial that we're going to use to approximate. And remember, x is 0.1. So then if I plug in 0.1, zero point 0.095308 is what we get for that. And then if we're going to calculate the error, we're going to use n plus 1. So we were doing the 4th degree, so now we're going to do 5. So R4 of x, our remainder, so remember that u has to be between c and x. So this part right here is if we take the fifth derivative of x, so taking this one more time gives us 24 over x plus 1 to the fifth. Well, that is less than 24, because if I plug 0.1 in here, I'm going to get a number smaller than 24. So that's what we can plug in for our f right here of u. So we know that that remainder has to be smaller than 24 over 5 factorial and then 0.1 to the fifth. So I'm just plugging in everything into here. I'm plugging in 24 for this because we know the remainder has to be smaller than that, and I'm plugging in 0.1 to the fifth in here, and that is approximately 0.00002. So that would be our upper bound for our error. Our error is at most this much when we get that approximation for the natural log of 1.1. So again, the whole idea behind the Taylor polynomials is the farther out we go, the more derivatives we use to come up with our Taylor polynomial, the better the approximation. And then we can use the error. We can always figure out what the error, upper bound error has to be. The remainder has to be the upper bound of that by using the derivative of the next value and figuring out what that has to be less than.